In this video, we are going to take a look at the traditional and per VLAN spanning tree. We are going to talk about BPDUs, the bridge protocol data units. We are going to talk about the important spanning tree timers, the election of the root bridge. We are going to talk about the port roles and port states, and finally, what happens when we have a topology change in the network. There are two types of bridge protocol data units. These are the configuration BPDU and the topology change notification BPDU. The configuration BPDUs are by default sent every 2 seconds by the root switch. This is happening once the root switch has been elected. But during the election process, every single switch in the network will be sending BPDUs periodically claiming it's the root. I'm going to cover this in more detail once we talk about the root elections in a moment. These frames are sent to a specific multicast destination of 0180C2000000. In a case when we are using 802.1q trunks and we are using Cisco's proprietary per VLAN spanning tree, on all the VLANs, additional BPDUs will be sent to a Cisco-specific destination of 01000CCC CCCD. And I will show you this in a moment. Each of BPDUs contain various information, like for example, the configured timers on that particular switch, and so on and so on. But I want to point out that there are also two important flags in configuration BPDUs that are going to work in combination with the topology change notification BPDUs during the time of convergence. That means when something has changed in our network. These two flags are the topology change flag, the TC flag, and also the topology change acknowledgement, the TCA flag. And the second type of the BPDU is called the topology change notification, the TCN BPDU. These BPDUs are going to be generated by the switches that have experienced a direct change in topology. A direct change in topology is the link going down, that means from a forwarding to disabled state or from a forwarding to blocking state, or the link changing state to forwarding. I'm going to talk about the link state, the port states, in a moment. Almost all aspects of the spanning tree are controlled by 3 timers. These are the hello time, the forward delay timer, and the maximum age timer, sometimes also called the max age. The hello time, which is by default 2 seconds, is the interval between 2 BPDUs. This timer is used by all switches when they need to transmit the BPDUs. That means during the root election, this timer is going to be used by all the switches in the network. Once the root bridge has been elected and it's the only switch actually transmitting the BPDUs, this timer controls how often does the root bridge transmit the BPDUs. When there is a topology change and bridges need to send the topology change notification BPDUs, this timer also controls how often these are sent. In a case we need to transmit more than one, which doesn't happen very often. The forward delay timer is the time switch ports are going to spend in transient port states. The port states are something that I'm going to talk about in a moment, but this timer is by default 15 seconds. The maximum age timer is used to detect an indirect failure in the network. By default, it's 20 seconds and it controls how long will the switch preserve a copy of the best BPDU. The best BPDU is the BPDU received from the switch that is closest to the root from the receiving switch's point of view. All of these timers can be modified. They can be modified directly or indirectly using the diameter-based calculation. The diameter-based calculation is an indirect calculation of the timers based on the size of our network and certain assumptions set forward by IEEE in 802.1d document, which vendors, like Cisco for example, can use to determine the default values of the timers. Incidentally, the timer values that Cisco is using are the same as recommended by IEEE. Root bridge election is a relatively simple but crucial process in spanning tree. This process is always on, which means that switches can change which switch is the root bridge at any moment in time. I like to say that switches using the spanning tree operate in a permanent state of democracy because we always have elections going on. But how does this process work? Well, first of all, every switch in the network is eligible to become root. The only thing that it needs to do to become root is to claim to be the best switch for that role. How do switches do that? Well, they transmit the BPDUs, the configuration BPDUs. And in these frames, there is a field that identifies the transmitting bridge. When this value is the best value in the network, this bridge becomes the root. What constitutes the best value for the bridge? Well, the bridge identifier or the bridge ID. This is a composite value that consists of, generally speaking, two values, the bridge priority and the bridge MAC address. When we are using the per VLAN spanning tree in Cisco's world, there is an extension of the bridge priority which is called the extended system ID, which works by simply adding the VLAN number to the configured priority. The default bridge priority on Cisco switches is 32,768. The bridge MAC address that is going to be used for root election is called the system MAC address, which is usually also called the base MAC address, and it can be viewed on a switch. Which MAC address is this going to be depends heavily on the platform we are using. It's going to be different on fixed configuration switches, and it's going to be different on modular switches, like for example 4500s and 6500s. Let me show you an example of the root election. I will look at a very simple network consisting of three switches. I'm going to have switch 1, switch 2, and switch 3 connected in a triangle like this. I'm going to assume that all three switches in my network are using the default bridge priority of 32,768. What I also need to know for my root election is the system MAC address, the bridge identifier of all these three switches. I'm going to keep things simple. So here on switch 1, I'm going to use the MAC address of all zeros followed by 0010. On switch 2, I'm going to use the MAC address of all zeros followed by 0020. And on switch 3, I'm going to use the MAC address of all zeros followed by 0030. If I turn this network on simultaneously, that means no switches were up, I'm just going to my circuit breaker and I'm flipping the power to on. What's going to happen is when these switches boot, they're all going to start transmitting the BPDUs. Let's take a look at switch 1. So it's going to start sending BPDUs out of these two interfaces here. In these BPDUs, I'm going to have few important bits of information. These are the important bits, not bits, but important chunks of information, the important data in these BPDUs. The first one will be something called sender ID. Sender ID in spanning tree is really just the source MAC address of the transmitting port. The source MAC address will actually be the actual MAC address used by this port. This is not necessarily going to be the same value as our bridge identifier, as our system MAC address. It's usually going to be somewhat higher. So let's say that here, this port, let's call it port number 1, and let's call this port number 2, that the sender MAC address here is actually going to be 000000000011 for port 1, or 1, 2 for port 2. So this is going to be our sender identifier. Also, inside our BPDU, we are going to have the priority field, or the bridge priority field, which will be the default value that we decided to use here. We are going to have the bridge identifier, the bridge MAC address, and this will be our system MAC address. And these two values here are going to form the information about what our bridge identifier actually is. And finally, we are going to have the information about the root priority, and the root MAC address. These are going to be the system MAC of the root bridge, and we are going to have the system priority of the root bridge. So I just wrongly wrote that down. So we are going to have the priority of the root, and we are going to have the system MAC of the root here as the value, and these two values here are forming something that we call the root identifier. So let's take a look at which values are going to be transmitted by switch 1 to switch 2. The sender ID, let's call it SID, is going to be the MAC address of the port number 1. So this is going to be all zeros, followed by 0011. We are going to have the bridge ID, and this is going to be our priority, 32,768, followed by our MAC address, and finally we need to see who the root is. By default, when the elections start, every single bridge claims to be the root. So switch 1 is going to claim to be the root. So this value here will be exactly the same as our own bridge identifier. The similar values will be transmitted to switch 3. The only thing that will be different will be the actual sender ID. Independently from switch 1, switch 2 is going to transmit its own BPDUs out of its own ports 1 and 2. So let's say that this port here is port number 1, and this port here is port number 2. So this is 2, and this here is port number 1. What are going to be the values there? Well, the sender ID is going to be all zeros, 0, 0, 2, 1. The bridge ID is going to be priority, followed by my own system MAC address, and the root ID is going to be my own bridge ID. Remember, this is the BPDU that was sent before we have actually received one from switch 1. So all these that I'm writing down are happening simultaneously. So here we are claiming to be the root ourselves. Oops, sorry, slight mistake there. This needs to be 20, just like this. So now these BPDUs are seen by switch 1 and switch 3. Remember, the one sent to switch 3 will just have this value here slightly different. Now let's take a look at what happens on switch 3. For this, I need to disappear a little bit. Switch 3 is also doing its own BPDU transmissions, and let's say that this here is port number 2 and this here is port number 1. So what switch 3 is going to do, we are going to have the sender ID, let's say for the frames going to switch 1, so going over this link here. We are going to have the sender ID is going to be all zeros, well, not really all zeros. This one here needs to be number 3. So 3, 1. Then we are going to have the bridge identifier, which will be the priority, followed by our own system MAC address. And finally, we are claiming to be the root as well. So now, when these switches have transmitted their initial BPDUs, switches have heard from each other. So what needs to happen here now is the actual election. So let's take a look at the example again. So we have switch 1 here, switch 2 here, and switch 3 here. They are interconnected like this. The initial BPDUs have been exchanged. I'm going to keep things simple. I'm just going to, here for switch 1, say that the important part of our bridge ID is really 1, 0. On switch 2, it's 2, 0. And on switch 3, it's 3, 0. I'm basing these values here based on these numbers here. So this is the only thing that I really care about. So 1, 0 for switch 1, 2, 0 for switch 2, and 3, 0 for switch 3. Once the BPDU from switch 1 is received by switch 2, switch 2 is going to see that, first of all, priority is the same. So it's 32,768. So priority here doesn't really come into play because it will be the same on switch 1, switch 2, and switch 3. So what we are going to look at are the MAC addresses. If the receiving BPDU is superior to our own, and by superior BPDU we mean better BPDU, and in spanning tree, lower value equals better always, this BPDU received from switch 1 on switch 2 is actually going to displace our own claim to the root. So at time interval 2, switch 2 is not going to be sending its own BPDUs. What it's going to do instead, it's going to take a copy of the received BPDU from switch 1 to send to switch 2, and it's going to transmit it to switch 3, with one slight difference. The sender ID will be the identifier of this port here. The bridge ID will be the identifier of switch 2, but the root ID will actually be whatever switch 1 has claimed there. Once switch 3 receives the frames from either switch 1 or the BPDU sent by switch 2, a similar process is going to happen on switch 3, which means that this value 30 is going to be displaced by the information from switch 1. In other words, switch 1 has won the election. It will be the only switch in the network actually transmitting the BPDUs, while switches 1 and 3 are just going to be retransmitting them, changing the sender ID, the source MAC address of the sender, to their own, and also inserting their own bridge IDs there. But what happens if we add the fourth switch? Let's say switch 4 here, with the system MAC address that looks like this. As you can see, the important bit of this MAC address is 04 here, which makes it better than this value here. When this happens, and when switch 4 starts transmitting its own BPDUs, these are going to become the superior BPDUs. So these BPDUs are actually going to win. So switch 4 will almost immediately, upon its own initial transmissions of BPDUs, become a root. This is what I meant when I said that the elections are always on. in the spanning tree. But really, this is it. This is how spanning tree elections work. Now, let me show you this on a real example. In this example, I'm going to use a very similar but slightly simpler network than the one I used before. So I'm going to use two switches, Cat1 and Cat2. I will also have a switch 3, my Cat3, but I'm not going to be using it to begin with. I'm just going to visit it a little bit later on. Cat1 and Cat2 are interconnected on ports Fast Ethernet 024, like this. And Cat2 and Cat3 are interconnected on Fast Ethernet 20. I also have my Wireshark monitoring station connected to Cat2 and connected to Cat3. In both cases, this is on Fast Ethernet 03. I have made sure that if all the interfaces interconnecting these switches are up, Cat1 becomes the root. I've done that by increasing the root priority on Cat2 and Cat3. Let me show you the exact configuration that I used here. So going to my terminal, on Cat3, if I do show spanning tree, I'm going to see here that the root ID says, that the bridge ID says that the priority is 61,441, but this is also going to be the root ID because the interface connecting Cat3 to other switches is down. So if I take a look at show interface FastNet 20, I can see that this interface is administratively down. And this is the configuration of my spanning tree. This was the command that I used to increase the priority. So I simply said spanning tree VLAN 1 priority 61,440. Remember, we are using per VLAN spanning tree by default here, which means that this configuration applies only to VLAN 1. It does not apply to any other VLANs, but this is okay. On Cat2, this is the situation as I have it right now. If I do show spanning tree, I'm again going to see that Cat2 is claiming to be the root, but the priority in this case is 57,345. If I do show run include spanning tree, this is the configuration that I'm going to see here. On Cat1, I'm simply using the default configuration of 32,768, and if I do show spanning tree on Cat1, I will see that Cat1 is claiming to be the root, and I can see that the default priority here is 32,769. Why is it not 32,768? Is because of the system ID, because of the extended system ID, where the VLAN number, in our case number 1, will be added to the actual base priority. So this is the setup that I have right now. What I'm going to do next is I'm going to go and configure on Cat2 a monitoring of traffic from port Fast Ethernet 24 to my Wireshark. I want to export the copy of these frames to my Wireshark, and I want to be able to capture these frames, so when this interface comes up, when I bring it out of shutdown, I want to see what is happening. I want to see the actual election process happen. Now, mind you, when I do that, it's going to happen very, very fast within the first frame. I may actually need to capture it more than once, depending on which switch was the first to send the frame. I think I can cheat a little bit there, so I will just show you my successful attempt. So what I'm going to do now is I'm going to go to Cat2 and I'm going to say monitor session 1, source interface FastNet 24. I want both incoming and outgoing frames captured, and I'm going to say monitor session 1 destination interface Fast Ethernet 03, and I want to preserve any VLAN tags if I have them. I'm now going to go on R2 to interface FastNet 24, and I'm going to prepare it to go out of shutdown, but I'm not going to do no shutdown yet. I'm going to go to Wireshark and I'm going to prepare a display filter to show me only the spanning tree BPDUs. Then I'm going to start the capture in my Wireshark, and now I'm going to bring the interface out of shutdown on Cat2. Now I'm going to go back to my Wireshark to see what got captured. As you can see here, what happened was spanning tree root election. Let me explain that. The highlighted frame here, 001906175889A, this is the source address of the frame. This is coming from Cat2. Then we can see this frame here from the source 00190610C5E9A. This is coming from Cat1. How do I know that? Because I remember that I made sure that Cat1 will be elected root. And take a look at all the subsequent spanning tree frames here. They're all coming from the same source. They're all coming from Cat1. But let's go back to this original frame here. So this frame was sent when the port initially came up. Take a look at a couple of things here. The first is the root identifier. Let me expand this a little bit. I can see the root bridge priority. This will be the same root bridge priority that was configured on Cat2. And here I have the extended system ID. Also, I have the root bridge system ID, which is 001906175880. Let me go back to my Cat2 here, and I'm going to do show version include base, and I'm going to see the base Ethernet MAC address, which is going to be the same MAC address that is being used for my root bridge identifier. So this here is Cat2 claiming to be the root. I can also see here that the bridge identifier carries pretty much the same information as the root bridge identifier. This was when the port initially came up. But then Cat1 started transmitting its own BPDUs. And here we can see that Cat1 is actually claiming to be the root. We can see the root identifier and the bridge identifier, which seem to be identical. If I take a look at all the subsequent frames here, they're all claiming to be coming from the same root. They're coming from Cat1. So Cat2 now stopped transmitting its own BPDUs. But let's go back to our terminal here. And what I want to do now is I want to bring in to the mix my Cat3. Before I do that, what I'm going to do is I'm going to start capture of traffic on Cat3. Now here, I'm seeing some traffic. That is because I forgot to do one thing. I forgot to set up the monitoring on Cat3. So what I want to do on Cat3 is I also want to capture the traffic from this interface here and send it to my Wireshark. But this is what I haven't configured yet. So let me just very quickly configure that on Cat3. So I'm going to say monitor session 1 source interface fastnet 20 both, and I'm going to say monitor session 1 destination interface fastnet 03 encapsulation replicate. So now if I go to my Wireshark, I'm just going to restart the capture here, and I'm going to show just the spanning tree frames. Now what I'm going to do, I'm going to bring Fast Ethernet 20 out of shutdown. And I'm going to go back to my Wireshark to see what is happening there. Now, take a look at this. I'm receiving some frames here. The sender, the source MAC address, appears to be something that ends with 5A96. If I go to my Cat2, and if I do show interface Fast Ethernet 20, I'm going to see that this appears to be the interface facing Cat3. So what I can see here in my frames received on Cat3 is that the source MAC address of the BPDU frames being received on Cat3 appears to be this interface here. This is my sender ID. So going back to my Wireshark, here, let's take a look at a couple of other things. First thing, the bridge identifier. Take a look at this value here. This is the bridge ID of Cat2. The reason why this is the bridge ID of Cat2, so bridge ID here on this BPDU frame being sent to Cat3 appears to be Cat2. This is the regenerated BPDU frame. Remember, Cat1 is our root, it's sending BPDUs to Cat2, but Cat2 needs to propagate them over to Cat3. So we can see information about Cat2 in these BPDUs. So these are not original BPDUs being forwarded out through the network. They're actually being flooded through our network. The difference between forwarding and flooding is that forwarding is happening strictly in the data plane. As soon as the frames are arriving, they're being switched out without actually, with switches actually not looking into the contents of these frames. With flooding, we need to accept the frame, we need to process it locally, we need to send it to the CPU for processing, we need to regenerate the frame and then send it out. So this is being flooded throughout our network. So bridge identifier here will be that of Cat2, but if you take a look at the root identifier in this frame being sent from Cat2 to Cat3 seems to be the root ID or the bridge ID of Cat1. So this will be the root ID that is being sent out on the BPDU sent to Cat3. So with this example, hopefully you can now understand how the election happens and how quick it actually is. If I go back to my Wireshark here just so I can illustrate how quick it was. So here it is. This was the second frame that was captured. Let me remove, so I'm going to stop this and I'm going to remove the filter. The first frame that was captured here was that of CDP. So the very, very first frame that arrived was spanning tree coming from Cat2. And with this, we can see that Cat3 didn't even have time to generate its own BPDU. The election happened almost immediately, before Cat3 was able to actually generate its own frame. So spanning tree is not that slow to elect the root. It can happen very, very fast. So this was the spanning tree root election. Once the root bridge has been elected in our network, the switches still need to calculate the loop-free topology. To do that, each port in the spanning tree domain will be assigned a specific port role. There can be 3 roles: the root port, the designated port, or the blocking port. The root port is, generally speaking, the port that has the lowest cost to reach the root. And this is where I'm going to introduce the concept of the cost. By default, the cost is based on the bandwidth, and on this table here, we can see just some common values of cost to bandwidth mapping. For example, on a 10 megabit interface, we are going to have by default cost 100. On a 10 gig interface, we are going to have cost 2. 1 gig will have cost 4, and 100 megabits per second will have cost 19. Please keep in mind that these are the values that apply only to the traditional spanning tree and per VLAN spanning tree. Different implementations of spanning tree use different mappings there. I'm going to talk about it when I talk about those different flavors of the spanning tree. We can also set the cost manually. We don't have to rely on bandwidth. This can be done on per interface basis. So going back to our root port. The root port will be the port that has the lowest path to the root. What I mean by that? Let me show you that. So I'm going to go to my whiteboard and I'm going to remind you about the example that we had earlier on with our 3 switches: switch 1, switch 2, and switch 3. We determined that switch 1 in our network will become the root because of the lowest MAC address there. So I'm just going to mark that switch 1 is the root. When switch 1 sends the BPDUs out of its 2 ports here, it is going to advertise the cost to reach the root. Because switch 1 is the route itself, the advertised cost, the cost that is going to be sent in these BPDUs, is going to be 0 in both cases. So when these frames reach switch 2 and switch 3 on these interfaces, they are going to see that the cost to reach the route out of this interface here is 0 plus their own configured cost here. If these were all, let's say, fast Ethernet interfaces, the configured cost here would be 19 and the configured cost here would be 19. In this case, our cost to reach route will be 19 on this port and 19 on this port here. But then when switch 2 sends the frames out towards switch 3, the advertised cost here is going to be switches 2 cost, which is going to be 19. When this frame arrives to switch 3, where we have 19 cost as well, in this case, the cost to reach route from switch 3 out of this interface here will be 19 plus 19, which is, you are guessing, higher than 19. So using this simple calculation here, we can determine that this interface here, facing the route directly, facing switch 1, will become the route port on switch 3. Similarly to this, this is going to become the route port on switch 2. So this is how the route port is determined. But let's go back to our presentation here, and I see that the next thing that I have to talk about is the designated port. The designated port will be the port on a shared segment that has the lowest advertised cost to the route. As opposed to this, blocking port will be any port on the shared segment that has the advertised cost to reach the route higher than the designated port. So we can have only one designated port per segment. I forgot to mention one thing when I talked about the route port, so let me just briefly mention it now. You can have only one route port per switch. All other ports on the switch must be either designated ports or blocking ports. But going back to our example here, we seem to have a problem with this. If all links here are fast Ethernet links, as I mentioned, that means that all links will have cost 19, which we can see on our example here. That means that both BPDUs sent by switch 2 on this segment and switch 3 on this segment will have the same advertised cost to reach the route, which would be 19 plus 19. Cost is just one of the tiebreakers, one of the parameters that can be used to determine this. There are actually 4 of them. The first one that is going to be taken into account is not actually going to be the cost to reach the route. It will actually be the lowest route bridge ID. But if we have 2 different bridge IDs, route bridge IDs mentioned in our BPDUs, that means that the election isn't over yet. So this first step is kind of a pre-election state. We still need to go through the election, but let's assume that the election has been finished. The next thing that we are going to take into account will be the lowest cost to reach the route bridge. If this happens to be the same as in our example here, we need to go to the next tiebreaker, and this will be the lowest sender bridge ID. You remember that in BPDUs we have that field, which is the bridge ID, which is a composite value that consists of the locally configured bridge priority and the MAC address, the system MAC address in use. So here, between switch 2 and switch 3, we are going to have the situation that switch 2, which, if you remember well, had the MAC address configured, or it was using the system MAC address that looked like this, and switch 3 had the MAC address that looked like this. In this case, switch 2 will win on this segment here. Why? Because of this value here, because it's lower than this value here. So this tiebreaker, the lowest sender bridge ID, will win. But there are situations when this is not enough. Imagine a network that looked like this. We have switch 1, which is the root. Then switch 1 is connected to switch 2, which is connected to a hub. But it's connected with two interfaces to a hub. Not only one interface, but two interfaces. And this hub is connected to switch 3. Now, let's look at the BPDUs as they are arriving. Switch 1 sends a BPDU. Switch 2 sends 2 copies of the BPDU, and both of these BPDU copies are arriving to switch 3. Now, let's take a look. Is the root ID going to be the same in this case? So root ID, is it going to be the same? Yes. What about the sender bridge ID, or the cost to reach the root? Assuming that all the links on switch 2 and switch 1 are of the same speed, the cost will be the same. What about the sender bridge ID? The sender bridge ID in this case, as perceived by switch 3, will in both cases, in case of this BPDU and in case of this BPDU, will be the same. In this case, we actually have to go deeper and identify the sender ports. So if I go back here, I'm going to see that the next tiebreaker is the lowest sender port ID. The port ID, similarly to bridge ID, is a composite value. It consists of the port priority and the port MAC address. Again, the lower value is preferred. One of the very dangerous situations when dealing with spanning tree is creating the loops that are not lasting forever, that are temporary in nature. They can still bring down the network, and they are very, very hard to troubleshoot because they are transient in their nature. To avoid this and to be more efficient in its operation, the spanning tree ports are not immediately just going to start forwarding the traffic the moment they come up. They're going to go through a series of transient states before we can actually transmit the data traffic through them. The port states in traditional spanning tree are disabled, listening, learning, forwarding, and blocking. Disabled port is the port that is either unplugged or shut down. Listening port is the port that doesn't send or receive any production data. It is not going to be transmitting the traffic, but it can still send and receive the BPDUs. Also, this port will not participate in MAC learning process. The learning port, the port that is in a learning phase, is not sending or receiving any production data. It's not transmitting or receiving traffic, but it is going to be sending and transmitting BPDUs, but it's also going to be learning the MAC addresses. The reason for learning phase to exist is to avoid unnecessary unknown unicast flooding. You may remember that process from one of the earlier videos. And finally, we have a forwarding port. Port that is in forwarding is sending and receiving data, it's sending and receiving BPDUs, and it's learning the MAC addresses. The blocking port is a port that is not forwarding, obviously, but it's also not shut down. This port is not sending or receiving any production data, and it's not sending any BPDUs. It's only listening to BPDUs, and this port is not learning the MAC addresses. Let me guide you through a process that port goes through when it comes up, and I will explain these states, the disabled, listening, learning, forwarding, and blocking, in a little bit more detail. Let's start with a port that is in a disabled state. When a port is in a disabled state, it's either shut down or unplugged. Let's say that this port is brought out of shutdown. When this happens, this port is immediately going to transition into a listening state. In the listening state, the port is going to start transmitting the BPDUs, and it's also going to be listening to the BPDUs that are coming in. Based on the incoming BPDUs, the port needs to make a determination here. If it receives a superior BPDU, and let me put this in here, that this is the check here for the superior BPDU. And the superior BPDU is the BPDU that goes through one of those tiebreakers and is determined to be better than the one that would be generated by this port. If we receive a superior BPDU, the port is going to transition into a blocking state. So if we receive a superior BPDU, we are going to transition into a blocking state. If we receive an inferior BPDU, or we are not getting any other BPDUs, the port is eventually going to transition into a learning phase. In a learning state here, we are still going to be performing checks, verifications, whether we are receiving superior BPDUs or not. So I'm going to add one more check here for a superior BPDU. If we receive a superior BPDU, again, we are going to transition into a blocking state. If we don't receive any superior BPDUs, eventually this port is going to transition into a forwarding state. In the forwarding state, the port is going to be transmitting and receiving production traffic, and it's also going to be receiving BPDUs. If at some point the port receives a superior BPDU on this segment, it is actually going to transition back to blocking state. So we can say that here, during the forwarding phase, there is always going to be this check here. Are we receiving superior BPDU? If you're not receiving superior BPDUs, we are still forwarding. If you receive a superior BPDU, we are going to go back into the blocking phase. In the blocking phase, there is also a check for superior BPDUs. Are we still receiving these superior BPDUs? So let's add a check here. If we are receiving superior BPDUs, we are going to go back into the blocking phase. But if we stop receiving our superior BPDUs, if they disappear, we are going to transition into a listening phase. So we are going to go back and listen for BPDUs. We are going to try to transition to the forwarding state. But these transitions between states, between the listening to learning and forwarding and blocking, are not immediate. So what is happening here, that when the port is in a listening phase, it is going to spend forward delay time in this phase. Once the forward delay timer expires, we are going to transition into a learning phase. And again, learning phase is going to last for forward delay time. Once we transition to the forwarding state, this is a stable state. So we can say that forwarding is a stable state. We are going to be there until we receive a superior BPDU. Listening and learning are transient states. Disabled, we can also say that it is from a standpoint of spanning tree, a stable state. If port is shut down, port is shut down. We have to do something to take it out of there. Also, blocking is a stable state. As long as we are receiving superior BPDUs, we are going to remain in this state. But if we stop receiving BPDUs, how long time needs to elapse before we transition to a listening phase? Well, this is where our max age timer comes into play. If we stop receiving superior BPDUs for a max age time, remember what max age is. How long we can keep a superior BPDU stored. So this is it. If you're no longer receiving a superior BPDU, for the max age timer, we are going to transition to the listening phase, and we are going to try to transition the port into a forwarding state. But if at any point here we receive a superior BPDU, we are going to go back into a blocking state. Let's take a look at how spanning tree handles the changes in the topology. To do that, we first have to define what constitutes a topology change. Well, there are two kinds of topology changes in the spanning tree. We have a direct topology change and an indirect topology change. A direct topology change is a condition when a port transitions from a forwarding state into a blocking or disabled state, or it transitions into a forwarding state from one of the other states, in most cases from a learning state. An indirect topology change is a condition when a switch stops receiving superior BPDUs on one of its ports. When this happens, the first thing that needs to happen is that the max age timer needs to expire. Once the max age timer expires, that means that we have not been seeing the superior BPDUs for the duration of the max age. We can signal, or we can say that the switch is experiencing a topology change. Once the switch is experiencing a topology change, either direct or indirect, it needs to inform the rest of the network about that. It is going to do that using the topology change notification BPDUs. These are going to be sent out of the root port every hello time for the duration of the forward delay time. Are you confused yet? Well, let me use the real numbers here. The default value for the hello time is 2 seconds. The default value for the forward delay is 15 seconds. When a switch experiences a topology change, it is going to be sending topology change notification BPDUs every 2 seconds for up to 15 seconds. But it may not end up transmitting more than one, because when the switch transmits this topology change notification BPDU out of its root port, it is going to be received by the upstream switch. The upstream switch is going to repeat the process. It is going to regenerate this topology change notification and send it out of its root port. During this time, the root switch, which may not be related to these two switches, is going to be sending its configuration BPDUs every 2 seconds. When the upstream switch receives the first configuration BPDU after it has received a topology change notification from a downstream switch, what it's going to do, before it regenerates this configuration BPDU towards the downstream switch, it is going to set the topology change acknowledgement bit to 1 in that configuration BPDU, and then transmit it to the downstream switch. When the downstream switch receives this configuration BPDU with the TCA bit set to 1, it is actually going to stop transmitting the topology change notification BPDUs. Why? Because this informs the downstream switch that, okay, someone has heard that it has experienced the topology change. There is no need for it to continue transmitting this. Now, this topology change notification BPDU that was originally generated by the downstream switch, by the switch that actually experienced the topology change, is going to flow upstream towards the root. Once it reaches the root is going to stop regenerating this BPDU. It's not going to be sending it downstream from itself, away from the switch that experienced the topology change. What it's instead going to do, on the next BPDU it sends, on the next configuration BPDU it sends, it's going to send the topology change bit to 1, the TC bit to 1. This will signal all the switches in the network that somewhere a topology change has happened. When the switches received the configuration BPDU with the TC bit set to 1, they're going to lower their aging timers, their MAC aging timers, down from the default, which on Cisco is 300 seconds, to the duration of the forward delay. The forward delay by default is 15 seconds. Now, the topology change bit being set to 1 and sent on the configuration BPDUs by the root switch is a condition that is going to exist in our network for the duration of the max age and the forward delay combined, which means 35 seconds by default. I would fully understand if you told me that you lost me somewhere halfway through that explanation. So let me show you an example in the whiteboard. Imagine that we had a network that had a switch 0 here. That was our root. And to this switch 0, we had 2 branches of switches. Let's call this one switch 1, 2, and this one here switch 1, 1. this branch here is branch 2, so I'm going to call this switch 2, 2, and this one here is going to be switch 2, 1. And also there is a connection between switches S11 and S21. This is the converged spanning tree topology. On switch 0, we have 2 designated ports. On switch 1, 2, this is the root port, and on switch 2, 2, this is the root port. This is a designated port, this is a designated port, this is a root port, this is a root port. Now, for this link here, let's assume that the lower switch number means the lower cost, the lower priority, the lower bridge ID. So this here would be a designated port, and this here would be a blocking port. Now, let's say that to switch 1, 1, we have some host A connected. What is happening in this network is that every 2 seconds, every hello time, root is generating, our switch 0 is generating configuration BPDUs. These configuration BPDUs are propagated as such. So this is a configuration BPDU. So it's being sent here, it's being sent here. Technically speaking, it is going to be sent towards host A, even though host A will have nothing to do with this. And this is sent on this link here. We are also having these BPDUs sent in our branch 2. So let's just write that these are configuration BPDUs. Now let's say that this link here fails. The link between switch 1, 1 and host A has failed. This was the link that was participating in spanning tree, even though host A may not have been running spanning tree, but switch 1, 1 was actually sending BPDUs there. Now it no longer can send the BPDU, so this port actually transitioned from the forwarding state into a disabled state. So what's going to happen here is immediately when this happens is switch S11 is going to be sending the TCN notification. So there is going to be a TCN BPDU sent out. So this here is the TCN. Now remember that these configuration BPDUs are still arriving. When switch 1, 2 receives the TCN, on the next configuration BPDU that it sends out, it is actually going to send a TCA, the topology change acknowledgement bit. Also, this TCN is going to be propagated towards the root, so there is TCN going up there. And similarly to the previous example, once the root receives this, it is going to set the TCA acknowledgement bit on the next configuration BPDU. Once the root receives this, what it's going to do, instead of forwarding this down this path here, down this tree here, and it won't do that because these are designated ports here. This is a designated port. Remember that the TCN is only sent out of the root ports. There are no root ports on the root bridge, so it doesn't require any special logic. Simply, there are no root ports, so we are not going to send the TCN BPDU anywhere. But instead, what it's going to do, instead of just sending a simple configuration BPDU, it is going to send, let me just use a different color here, it is going to send the TC bit set on these configuration BPDUs. So here as well, and here as well. Once any of these switches receive the TC bit set to 1, what this is going to do on this switch here, it is going to lower the aging timer from the default to the duration of the forward delay, which by default is 15 seconds. I hope this clarified a little bit the topology change procedures in the spanning tree. In the next video, we are going to take a look at the configuration of the per VLAN spanning tree.